Hi everyone, let's get on to another question. So once again we have been given a binary tree, and this time we want to convert it to its mirror image. Okay, so guys, this is a very popular interview question and I hope all of you understand what a mirror image looks like. So just pause the video for a while and think how mirror image of a binary tree would look like. Let's just do that. So let us take a quick example. So let's say our input binary tree is somewhat like this: 4, 5, 1, 9, 6, and let's say 7. Now guys, if I place a mirror in front of it over here, what will happen? What does a mirror do? A mirror performs something called as lateral inversion. And what is lateral inversion? It makes left appear in right and it makes right appear in left. Coincidentally, the concept of left and right is very closely coupled with binary trees. Left is the left subtree and right is the right subtree. Okay, left subtree is rooted at 5 and right subtree is rooted at 1. So what will happen is that for this node 4, the left subtree will appear in right and right subtree will appear in left. So I can say that the nodes which are children will get interchanged, right? So what will happen over here is that in its mirror image for 4, this one which earlier was a right child will now appear as a left child. Similarly, this 5 which earlier was a left child will now appear as a right child. But guys, do you believe this thing will happen only for 5 and 1 which are children of 4? Just pause and think. So guys, we will realize it here that this interchanging of left and right children will not only happen for node 4, but it will happen across all the nodes. What I mean by that is, when you come to this one, the left child of 1 is null and right child is 7, and they also will get swapped. So 7 will now appear as the left child and null will now appear as the right child. I'm not drawing that. Similarly here for this 5 also, this 9 and 6 which are the left and right children respectively will get swapped and it will start looking like 6, 9. So this is how the mirror image of this thing will look like. So guys, it looks like there'll be a very simple code written for this. So just pause and imagine it in your head that how the flow of the code will look like. Okay guys, an important thing to take care of here is that we do not have to create a new tree. Okay, so no further extra memory allocation is required over here. We have to transform the same tree in place. Okay, interesting thing to note again is that in this entire process, the root is not going to change. So the address to the root node won't change. So I need not write a function that returns me updated root or something like that. I can simply write a void function which performs the transformations needed, and once those transformations are done, it can just exit. Okay, so that way I can get it done. Now here the flow of the code can be imagined in this manner. So let's say you write a function called as mirror. This function takes node of a tree whose mirror image it is trying to construct. The first responsibility will be to swap the left and right children. That will be the first thing. But the game is not over yet, because now I need to repeat the same process for all the other remaining nodes. And how to do that in case of trees? Just make a call to the left subtree and another call to the right subtree. So I can recursively call this function for node left, which is the root of my left subtree, and I can also recursively call the same function for node right, which is the root of my right subtree. So that's it, job done, right? And what will be the termination condition again? Just pause and think. So guys, whenever we encounter that a node is null, it means that we are trying to create mirror image of a tree which is empty. So there is nothing which is required to be done. So you can just exit in that case, right? So once it is clear, we can now go ahead and try writing the code of it. So guys, there'll be a function called as mirror, and this function will take root of the tree that it is trying to convert into its mirror image, right? Now, the first logic can be, if root is null, it means that your tree is empty, so nothing is supposed to be done, just return. Otherwise, you need to swap these two things. Now, whenever you swap two things, you do that by using a temporary variable. So here I can have a temporary variable of the same type node star, and what I'll do is, first inside it I'll save the address of left, root left, and after that I'll change my root left to become equals to root right, and then I'll change my root right to become equals to the actual value of root left, which was stored in temp. So this part is done. Okay, this part is done, swapping is done. Now I just need to make a recursive call over my left subtree, which is rooted at root left, and then I can call for my right subtree. As simple as that. So guys, in this approach you will see, let's say you called at 4, the first thing you would end up doing is you would make the left child of 4 as 1, and you would make the right child of 4 as 5. Until now you have done nothing with the children of 1 and 5. So 1 will continue to have a right child of 7 and left child of null, and similarly 5 will continue to have a right child of 6 and left child of 9. Now when you invoke mirror image function over this part, then it will make sure that it swaps the children of 1, which is null will appear here and this 7 will appear over here. Okay, now again when you call over here at this particular node, it will swap the left and right children of 7, which are null and null, so there will be no effect. Okay, and then when you call from 7 to null, you will just terminate, and then recursion will come up, then again up, then it will be called here, and then it will perform a swap of the 6 and 9, and then it will call at 6 where it will swap null and null, so nothing will happen. So again it terminates, comes up, then calls here. So that way your entire tree would end up getting converted into its deserving mirror image, and this process will just consume order n amount of time, because if you draw the recursion tree diagram, you'll again see that there are n function calls, and at every node you're just performing a swap operation and nothing else. Okay, so that is the idea behind this approach. And also space complexity is going to be order h, and that you can again be able to figure out when you look at the recursion tree diagram, which will just be this actual tree itself. Okay, cool.